It's my pleasure to have our IDS Distinguished Speaker, Series number 6, from Professor Eric Delage from the HEC Montreal. And here comes the 6th event under our IDS Distinguished Speaker Series. We are honored to have invited Professor Eric Delage, Professor in Department of Decision Sciences, HEC Montreal. Professor Eric Delage is a professor in the department. Was a while to repeat this. He's a chair of the Canadian Research Chair in Decision Making Under Uncertainty and a member of the College of New Scholars, Artists, and Scientists of the Royal Society of Canada. His research interest spans the area of robust and stochastic optimization, decision analysis, reinforced learning, and risk management, with applications to portfolio optimization, inventory management, energy, and transportation problems. Without further ado, let's have Eric to give our presentation. Thanks.
Thank you. Yes, do you hear me well? Everything's good? Thank you very much, Professor Yuma, for the generous introduction. Thank you for the Institute of Data Science for the invitation. I must also thank very warmly Wenjie Wang for organizing this visit. I think we've been talking about a visit of HKU since the world recovered from COVID, and finally there was some energy that was needed to really turn this into reality, and I'm really benefiting. I find it's a fabulous experience to be visiting your campus. So today I'll be presenting a talk. And I must say, I'm really honored about being part of your distinguished speaker. I hope that I'll live up to your expectation with respect to this series. The objective of the talk today is twofold. So first of all, I want to introduce you, if you're not familiar with it already, to the field of contextual optimization, which is a field that I've been myself interested in for a while, at least 6 years, and perhaps since even I did my PhD, it wasn't called this way, but we were trying to turn data into decisions, and this is really being summarized well with this notion of contextual optimization nowadays. In this regard, I'm part of a group in Montreal that have received a lot of funding to push forward initiatives on this topic, and one main accomplishment we did last summer was to build a survey on contextual optimization, which is now published in the European Journal of Operational Research. So today's talk, first objective is to introduce you to this field. I'll be presenting some of the main work and the main ways we can tackle the challenges in this field. And throughout the talk, I'll be including some achievements that my group has been bringing to this topic, especially the flavor that we give to our research projects have to do with making the methods risk-aware and robust to estimation error. Okay. I want to thank, of course, Canada Research Chair for the funding and allowing all this research, and also our own Institute of Data Science, which we called IVADO, which has been running in Montreal for more than 6 years. And they really enable all the research on these topics. I hope there's collaboration that could emerge from the Institute in Hong Kong University and the efforts in Montreal. So let's start right away with what do I mean by contextual optimization? What type of situation might require this type of technique? And I'm starting with a very naive and toy example here, which is a shortest path problem. So say you were trying to find the shortest route between point A and point B in a city. So here I could try to find the right route to follow between my house and one of the temples in Hong Kong. Well, the choice will depend on the travel time of each arc of the road network, and the path that I'll follow will probably be different in conditions where the temperature is good from conditions where the temperature is bad. So note here that we have incentive to adapt our decision about which route to follow as a function of conditions of the environment. So in the talk today, we'll be talking about contextual information like weather, that is available at the time where we're planning. And this information allows us to better understand the hidden random variable, which is Y here, the travel time of each of these arcs, which is not known before you actually traverse that arc. So if it's sunny, I might realize that some area of the city have good traffic condition. Maybe there's still some slowdown in some area if there's like a beach and people want to go to the beach. A lot of people accumulate in the streets and it creates congestion. If it's rainy, then things could be different. So some roads might be more slippery, creating people interested in going slower, or perhaps there's a likelihood of accidents, and this could affect the route that I decide to take if I am able to really make best use of the implicit information revealed by X. This is all a toy example, but in practice, this was studied in the work of Callus and Mao in 2022. In the shortest path problem, where we're trying to find the best path to follow from an east side to the west side of the city of Los Angeles at different points of time in the day. So you see that this is a shortest path problem, and the information that they were referring to as being meaningful for this type of decision included the period of the day, the temperature, wind speed, rain, visibility, and perhaps the calendar day. So weekends versus the day of the week, or perhaps there's special holidays that are affecting the condition of the traffic on the road networks. So we see here that very small differences in these conditions could affect the optimal route that we follow. So here going from in the morning, a path that traverses the city from above, to in midday, an optimal path traversing the city from below. Okay. Another application that is appeared very early in the literature and comes from a pioneering work of Ban and Rubin in 2019 is a nurse staffing problem in a hospital in the United Kingdom. So in this context, they were using information about the calendar, so day of the week, time of the day, and also a time series of the most recent demand observed in the hospital to plan the demand in the coming hours and have proper staffing decisions in terms of how many nurses need to be available in order to cover this demand. And so you see here in blue the realization of the demand, and in red somehow the plan that was made in terms of STURF in order to cover this demand. The final example is one that I've been dedicating more of my own time to, which is a portfolio optimization problem. So in a portfolio optimization problem, you're trying to invest in a certain number of assets. Here I give you the big four companies in the US, Google, Amazon, Facebook, and Apple. The pie chart tells you a plan. A plan here would be a portfolio composition. And we could think about what is the information we could use for planning a portfolio investment. Well, on the left, I have pictures from Yahoo Finance website that are describing the current reports for those companies. So you have things like the bid-ask spreads for the prices, you have historical data, you have the volume of how many purchases are being made at a certain point of time. You could also use text information, right? There's a bunch of Twitter feeds that are describing things happening about different companies, people commenting on the stock, and we would like to make all the use of this information at the moment of creating a portfolio. So whether you're delivering package, solving a shortest path, managing inventory, or building a portfolio, well, you might need to be better off trying to use as much as possible the information that is available at the time of making these plans. And this is what we call doing contextual optimization. And now I'll dive into a bit more of the math. So how do we model these problems? And if you've not worked with contextual optimization, you might already be familiar with a more simpler setting where here I'll call stochastic optimization, but people also call this stochastic programming. So in this context, the notation will be like in my slides. I have a cost that depends on my decision Z, which must be in a feasible set calligraphic Z. And this cost also depends on a vector of parameters Y, which was in my shortest path problem, the time to take to traverse each of these arcs. So in stochastic optimization, you want to minimize the expected value of this cost over the distribution of Y. Okay? So what happens in contextual optimization? Well, then you have information that is being revealed. And this information takes a form of X. If you look at the literature, this is also called covariates, or you might also call this features of the system that you want to exploit. So what is the optimal decision in this context? Well, it's the same as our stochastic programming, but we replace the distribution of Y that is uninformed by X by the conditional distribution of Y given X. Okay? So to be a bit more, even diving in more technicality, there's another form of optimization model that emerged in this context, which here I refer to as policy optimization or decision rule optimization. So we could just step aside and think about the problem before we even see X. And since this is usually the case also because of my portfolio problem, I might rebalance every minute. And so I have to think about how will I react to the information that is coming in the future. So in this setting, what we design is rather a mapping from the space of covariates to the space of action. And the way we quantify the performance of a policy, which I also refer as a decision rule, is by measuring the expected cost of this decision rule, but note that the expectation here is over the joint distribution of X and Y. So there are two models here. The models on the right is optimizing the conditional expected cost, but has to be optimized for every realization of X, while the model on the left is optimizing the unconditional expected cost. And I solve it once. This gives me a decision rule that I can apply on any realization of X. What's written on the bottom right here is that these are not disconnected models. They're actually solving the same underlying problem. And this can be demonstrated through the interchangeability property of expected value. So when you solve the conditional stochastic optimization problem, this gives you a good policy for the policy optimization problem. And vice versa, you can recuperate your solution to the condition problem by solving policy optimization. Yes. Yes, so in the talk I'll be referring to P of Y given X, and or capital P without any subscript is usually the joint distribution over both. Yeah. And in the talk, I'll be using this notation in 3 or 4 places where I refer to the conditional expected cost by lowercase h, while the unconditional cost will be capital H. Okay, but it just comes very sparsely. So what can we do in this context? We're interested both in the policy optimization and the conditional stochastic optimization. It's sort of the same problem. There are different methods. The first group of methods that we were able to identify in the literature is based on decision rules or policies. So this one will parameterize your mapping with theta, and it will try to find the best theta in terms of the performance of the policy on the data set, which is referred by the empirical distribution of the data set. The second approach will be sequential learning and optimization. So first you use the data set to train a model of your uncertainty, which is what? It's this operator here, f theta x, which when I plug in a new x in here, it's going to give me a conditional distribution for y, and it will adapt to the different covariates that I observe. This conditional distribution can be passed in our conditional stochastic optimization problem to produce our decision. More recently, there's been a lot of activity on the last framework that I'm presenting here. I think it's really interesting, promising. Theoretically, it's difficult to say a lot, but empirically, you'll see later that it accomplishes very strong performance. What is this paradigm saying? This paradigm is saying that instead of training your predictor in terms of statistical performance, we'll see what I mean by statistical performance in a moment, but just looking at the data and making the uncertainty based on when you look at the data, reasonable, yes, it seems to represent the uncertainty I see in my data. You make a predictor that produces decisions that perform well on your data set. So the shortest path problem will appear here and will be used to train the type of predictor that we're using for this task. Okay? So I'll come back to this last. I'll survey the 3 different frameworks. For the 2 first frameworks, I'll give you an example of what our group has done in the last 6 years. In the last example, I'll have a whole section to talk about how integrated learning and optimization can be used for robust optimization. And this I feel is really promising and is pushing forward what is currently done in contextual optimization, but from the point of view of a robust optimization model. Okay, so let's start with the first section, decision rule optimization. Okay, so first of all, ideally in decision rule optimization, you want to identify the best policy. And this policy is an infinite dimensional object. So the trick that needs to be applied is how do we make this a finite dimensional problem? And the first to do so were Ban and Rudin in 2019 with their famous paper, Big Data News Vendor Problem, where they considered the orders that would be made under a certain vector of covariates to be simply a linear combination of the covariates. Okay, so then we parameterize the policy by Q. This makes the problem finite dimensional. And then we measure the expected cost of our policy under the data distribution, or the empirical distribution from our data set. They argue that you should also include a regularization term, which here takes the form of the squared norm of Q. Okay, and this allows them to, provide finite sample guarantees. So the main contribution of the paper was to say, if you use lambda of a certain size, you're able to control the out-of-sample performance of your policy. And you can, and this out-of-sample performance is especially hard to control when the dimension of Q increases because you have a lot of covariates. Okay. The issue with this approach is because they use a linear decision rule, they cannot model any arbitrary function. So asymptotically, even if you have a lot of data, you will never converge to the best policy that you could find using this data. So on this side, we were very interested in 2017, me and my master's student, Thierry Bazier-Matt. We were interested in this method. This was just a preliminary draft we found on Archive or Optimization Online, and we started working right away on the portfolio optimization version of this, instead of the news vendor. So where in the portfolio, you have k different assets, so your portfolio will be a linear combination of the features of the asset. That's how much you invest in the portfolio. You multiply by the return you obtain to obtain your final return on your portfolio investment. We wanted to make this risk aware, like I said before. Risk aversion can be modeled using a utility function, which is concave here. So we employed the expected utility paradigm, and we were able to generalize the error bounds, the finite sample guarantees from the original paper to this setting. The issue with this setting is that the objective here was not upper bounded. And in the original result, they needed that the cost function be lower bounded. It's sort of a small detail, but still for a master's thesis, this was really interesting to work. And another aspect that was not in the initial paper of Bannon-Wooden was how to extend to nonlinear functions. And we identified that reproducing kernel Hilbert spaces could be used for that. It just so happened that Bannon-Wooden was actually also realizing that independently, and we both came up with similar approaches for that. So here's the example we applied it to, and we were really looking at a simple problem. So we have a portfolio that can invest in either in a risk-free or a risky asset. The risky asset here is takes the form of a NASDAQ index. So let's think about it as an ETF over the NASDAQ index. This is the evolution of the NASDAQ index value is going through the dotted line. And we're comparing two types of investment. One investment that uses historical data to know what's the right proportion to invest in that index and keep in the risk-free asset. And compared to an approach, a policy that is able to exploit volatility of the market. So what is volatility here? We look historically in the 60 days, what was the standard deviation of this index? And we would like to react to this value so that we somehow allow the investor to be protected against shocks when the volatility increases. And so we had a first proof of concept that you could learn directly from data a policy that would react to the volatility of the market. Namely, when the volatility goes up, the investment goes down. Okay? And this also allows to, in general, invest more in the NASDAQ index, although we're using the same risk aversion level. So we're able to be less cautious in general because we are careful in the moments that matter most. If you're looking at more of the literature on decision rules, well, you see a lot of effort into trying to make this function more flexible. So I've talked about reproducing kernel Hilbert spaces. So the two papers I've mentioned before. There was a follow-up paper by Berksimas and Koduri in 2023 that generalized this approach to an arbitrary, a more general cost function, and also models in which you've got uncertainty in the constraints. So they're able to work it out. Zhang et al. Worked on piecewise affine decision rules, and you see in the result there that they have evidence that it performs better than reproducing kernel Hilbert space. And finally, really, nowadays you might think, let's just put as a policy a neural network, where the parameters are just the different weights of all the layers of this neural network. And this was done in 2020 by Rouge Louis Ajdid for the news vendor problem. Now, what people criticize neural network for this task is that once you get the policy function, it's really hard to interpret. You don't know what's causing what in terms of the output of the network. When we think about this nowadays, we say, why did we regularize when we're doing stochastic programming, and nowadays, like the prevalent scheme for robustifying stochastic programming or stochastic optimization is distributionally robust optimization. And I'm especially well positioned to tell you about, yes, perhaps we should have thought right away to do DRO. I was already involved in that field. The issue is that in 2016-17, we didn't have the right ambiguity set to deal with these problems. We're working with moment ambiguity sets. Yet there was a breakthrough in 2018 with the paper of Moraes, Jarin, and Esfahani and Kuhn. We presented the Wasserstein ambiguity set, and many of you are in the room are familiar with this set. For those that are not, think of it as a set of distributions that is a ball in the space of distribution. The center of the ball is the empirical distribution, so the distribution of your data. And by sizing this ball, you're able to be more or less conservative with respect to variations away from that reference distribution. So we could look at our policy optimization problem from the robust point of view, where now we're measuring the worst case expected costs, with worst case being over all the distribution in this ball. Well, yes, this leads to interesting methods. You can use duality to reformulate this, solve this as a mathematical program. One thing that's really curious about the whole setup is that the result in 2019 from Shafizadeh Abadeh that establishes conditions where this DRO model reduces to regularization. So it just so happens that Ban and Udin, my student Bazimat and myself, we were all doing DRO unknowingly because we were doing a regularization with Lambda. The regularization we get from Wasserstein ambiguity set is the radius of the set times the Lipschitz constant of your cost function times the norm of Q. So very similar concept, just motivated from different, using different theories.
Eric,
yes.
Just a simple question. So for vector optimization, the lines, so how you, for arbitrary D, how you get for the previous lines, the last line, how this is arbitrary D. Q belong to D is arbitrary D.
No, I'm saying this D.
Yeah. So how you get a very simple forms? So the last one is very simple, right?
This is very simple.
How to rate it? So can you?
The intuition here is that when you're perturbing the reference distribution,
okay,
the adversary is able to push some weight to infinity,
okay,
but very small amount of weight.
okay.
So while staying within this radius, it's still able to go push the weights in the direction where the Lipschitz constant is the strongest. And this recuperates that the worst case distribution is really just adding this term to your expected value.
Oh, it's equivalent to a type of penalization.
Yes, exactly.
Thanks.
So I had announced I would talk about the three frameworks. I'm at the second framework at this point. Sequential learning and optimization. I think the best motivation to go away from decision rule to sequential learning and optimization is that decision rules have problems with constraint. So think about this neural network or this linear function. If I have constraints on what is the result of this linear operator, it really limits the type of parameter I can use, and in fact, it might make the problem infeasible. So to address this, one way is to consider that the decision comes from this conditional stochastic optimization. By construction, the output of this decision model is always feasible. Right? So you can think of this as a way of correcting. I can also motivate this by saying it's much easier to interpret the prescribed decision when you know what's the distribution model that was used to get the model itself. Okay? So let's look at what we can do. So we'll need different tools here. We need to find out how do we train this predictor. Right? This predictor, in the context of a conditional stochastic optimization model, needs to be a conditional distribution. So given X, what is the density for Y I should be using? So we'll use, I'm really giving you the broad terms. We take the data we convert it into a predictor of the conditional distribution, and this is done by minimizing some estimation error, so the error between the predicted density and the empirical distribution, in some sense, okay? How can we do this? In general, and here we say for nonlinear cost, because we'll see linear cost is specific, can be treated differently. F theta is a conditional density estimator, and one way of training it is through maximum likelihood. So what is this maximum likelihood doing? It's taking every data point, looking at what's the density for the x of that data point, and measuring the likeliness of the y point given x under that model. If you take the log and you take the average of everything, you'll get you'll get the likelihood, which can then be minimized in its negative form. So that can be used. It's very prevalent in the literature. One thing that is interesting, I talked about shortest path problem as a linear cost, right? My portfolio optimization problem as a linear cost. What happens when we have a linear cost? Well, look at the equation down here. We see on the left the conditional expectation of y transpose z under the predicted distribution. But linearity of expectation tells me that I can simply, I can push out the z from this expected value. These are constants in this expression. So I get the expected value of y under the density f theta x transpose z. So it's a little bit of a detour to be predicting a conditional estimation when the optimization model actually only use a conditional expected value of y, not the whole distribution. Right? Why learn the distribution when you only need to learn its mean? So you can learn the mean of a distribution simply by doing regression, least square regression. So in this context, we really just need a point predictor. We don't need a predictor of the whole density, the whole conditional distribution. This can be done using, by minimizing the mean square error between the predicted value and the observed value. Going back to conditional nonlinear costs, I told you how we can train these conditional distributions. Now we need to take into account the fact that we're going to be optimizing with these models. And optimization is difficult if the distributions have a density, if the random variables are continuous. There is at some point a need to discretize. So a lot of the literature have focused on forms of f theta x where the distribution is discrete instead of continuous. So here's an example that is rather simple. Given x, you'll have a bunch of scenarios, yi of x, and you're just putting 1 over n over all these scenarios. And you want to know what are the right scenarios to use. Okay? This can be done using what's called residual-based learning of the distribution. So what are you doing here? You're first learning from your data a prediction of y given x. This is my g theta x from my linear cost before. But now I want stochasticity. So I can inject stochasticity using some perturbation terms here, I, epsilon I. What are these? Well, when I do regression, I have the residual of my regression, meaning for every data point, I couldn't predict exactly the y. The difference between the two can be captured by epsilon I. And this tells me how much I should perturb my prediction so that it becomes stochastic, or so that it starts to look like the distribution of y given x. So there are some papers that are really interesting where they're exploiting this, trying to get from the residual information a way to perturb the scenarios of the point predictor. Another family of methods are revisiting this discrete distribution, and instead of changing the scenario, they're changing the weight of the scenarios that are observable in the data set. So if you have a data set going from 1 to n, you can put support points on these data points, but the question is how much weight should you assign to these data points? And the amount of weight you assign to data point I will be inversely proportional to the distance between x and the xi for this data point. How do we do this? We do this through the weight. Okay. Simple method, k nearest neighbor. So you get a new day for your shortest path problem. You look in your whole data set, what are the other data points that look like the conditions of today? What are the k other data points that are the closest to this new one? and I can put a uniform distribution over all these points. So this is a way of creating this weight operator. A method that is a little softer, it will make better use of all the data you have available, is to put some positive weights on all the data points, but perhaps the further the data point is from your current observed x, the less weight you put on that. And the notion of distance can be modeled using a kernel. So you could have a Gaussian kernel where the weight goes down at an exponential rate. Another family of methods, which we label as supervised learning methods, are training decision trees or classification engines in order to predict something. And usually when you train these approach, you have in mind predicting the conditional expected value of y given x, but the result of this training is to give you a tree, which is a classifier. It says, given a new x or any x, I have a bunch of rules I apply along the nodes of a tree, where every time I ask the question about x, I decide if I go right or left on a branch, and depending on the leaf that I obtain at the end, I'll get a different model for my conditional distribution. Okay, so in this case, like I won't go into the details, this is a bit more technical, but you'll see why later, why I'm introducing this technique. So R of x here is the leaf in which the covariate, the contextual information vector lands. I can look in my data set all the other points that land in the same leaf of the tree, and then use a uniform weight over all of them. A little bit like k nearest neighbor, but using less the notion of a neighborhood or distance, but rather the notion of a decision tree. If I use many decision trees, then I can average the weights over all of them. So why am I presenting these more sophisticated methods? So first of all, like this is what's available, and I want to give you already some ideas of the diversity of tools that can be employed. But also, I wanted to point this study. So it's very rare to see studies that benchmark a large number of different methods. So in this study, they benchmarked, there's a section where they benchmark exactly the type of method we've been talking about, going from decision rule methods, linear rule deep learning, to sequential learning and optimization method, like where you're using weights that are based on kernel weights, k nearest neighbor, or decision trees in random forest. Again, there are 4 different data sets. The bakery data set has to do with information that was obtained from a local bakery. M5 is a data set for a forecasting challenge that was announced by Walmart. Restaurant is a data set about an inventory problem for a restaurant that has to decide what will it unfreeze on the day before operation, trying to avoid spoiling the food. And SID is a data set that was on Kaggle about inventory management, but there was a competition for forecasting here too. A lot of information is here. The different columns for each of these graphs, they refer to variations of a news vendor problem. And for each of these variations, they drew a certain number of instances using the data sets, and they look at, for these instances, what proportion of instances were dominated by a specific method. So for instance, here it says that the blue method, which is random forest weights, was the best method for this proportion, which is probably something like 30% of the instances generated of this case. While the linear decision rule was much more often the best method to employ. And you see, I think here the conclusion is that random forest weights, although I didn't give enough time to introducing you to them, it's worth going to read about it, and they seem to perform very well. Somehow they're able to learn a metric on the X space that is very relevant and useful. Linear decision rule also performs surprisingly well for this problem.
Can we say the random forest weights is the best, and the linear rows is the second? So I mean the random forest weight is a kind of a lot of non-linearity, and the linear rows is linear. Mm-hmm. So any reason behind it? I mean the non-linear performs best. Second one is linear.
It's a good question. We would have to dig deeper into the data sets to find out. Perhaps it's a question of, in the cases where linear works well, linear decision rules are the approach that will perform best, but in nonlinear case, it seems like the 4 other nonlinear methods perhaps they have some catching up to do with respect to stochastic for us. But perhaps I would say, like, in some case, linear does very well, and when you cannot do well with linear decision rules, then random forest seems to be the best alternative based on this study. But I am not too sure what I suspect linear decision rule could be good in a context where the demand from previous day is very similar to the next day, and then you can simply multiply average previous demand by a certain scalar, and you get a good prediction of tomorrow.
I think a linear rule perhaps is already included reproducing kernel space, right? So that means you already involve a lot of nonlinearity.
Nonlinearity? I would have to double check, but I believe this is just linear rule. It's not on a lifted space and so on. Yeah,
Okay, thanks.
we can. Thank you for your question. Okay, so what did we do in this space? I'm presenting the model we were working with in this Nguyen et al. 2021. This is still a work in revision. The idea there was to robustify non-parametric conditional stochastic optimization problems. So forget about what's in blue here, which is just a DRO part component of the model for now. We want to minimize our conditional expected cost, but we use as the condition the fact that x is inside a neighborhood of our observed x. So we're relaxing this conditional stochastic optimization by allowing other x's to emerge. This approach embeds k nearest neighbor. So if you choose gamma properly, the distribution you would get here from if you use Q as the empirical distribution, would be the k nearest neighbor conditional distribution model. So what did we do here? We said, let's be robust to the choice of distribution. Instead of using the empirical distribution, we want to use a distribution in this Wasserstein ball. But what we realized very quickly is that if we allow the adversary to perturb both the density over both x and y, this adversary is able to push all my empirical data points outside my neighborhood. And if Q has zero probability in this neighborhood, this conditional expectation is ill-defined. It doesn't mean anything anymore. So we had to work with a specific type of constraint that emerged in this problem, where we have to make sure that the adversarial distribution has at least epsilon mass inside this neighborhood. Okay. This is a complex model. If you use as cost function the squared difference between z and y, it just so happened that you obtain a conditional mean estimation problem. And this led to a publication in NeurIPS, where we were treating with robustifying conditional mean estimation using exactly this model. So this was a precursor of the follow-up work, but a simpler setting where we're simply trying to predict the expected value of y given x, and this will be obtained by the minimizer for z, and we're robustifying using our ambiguity set. So I wanted to show you something more concrete. So, and I really like this work because it shows how contextual optimization is really at the boundary between optimization and machine learning. So what we discover for perhaps problems that are optimization driven or are driven could have implication for regression problems and machine learning problems. So here we revisited the handwritten digit estimation problem using the MNIST data set. So what is the contextual optimization problem here? We're trying to, our covariate is x. X is an image. So there's a lot of images in that data set. Each image is labeled by the number that has been recognized on the image. So given this image, we're trying to estimate the expected value of y given x inside a neighborhood of this image. Okay, and we use low data regime because that's where we expect robustification to really have the biggest impact. This simulates the fact that in general there are many data sets that you don't have a lot of data to work with, but you still want to make conditional estimation models. So we have on the right, bottom right, the performance of this approach in blue compared to two benchmarks. K-nearest neighbor approach is in green, and orange is another DRO method that puts an ambiguity set only on the distribution of y instead of jointly over x and y. So the graphs are the distribution function of the absolute estimation error. And what I want you to recognize here is that you see that the blue method is stochastically dominating the other two. Like for any level, it achieves a higher rate of achieving this performance. And especially at 0, this is an interesting location where we can see that there's zero error rate, zero error for 40% of the images in our test set, compared to perhaps 35 and 25. Okay, so we're able to more often exactly recuperate the label of the image than the two other methods. And we played with this, looking at images that could be artificially generated in a way that makes it look like very difficult to distinguish between the different numbers that could be associated to the image. This is done here by taking two different images and then doing an interpolation between the two images that is based on Wasserstein-Barycenter perturbation. So I spare you the details of this type of perturbations, but they're really meant to extrapolate, do a convex combination of the two vectors x, so that in between, they look a lot like both of them as you go from one to the other. So you see here a 6 becoming a 0, and there you see a 3 becoming an 8. I believe you agree with me that some of these are difficult to recognize, right? So here are the results here for these two types of, the two examples, where we see that the two methods, they seem to be good. So there are some situations where the perturbation doesn't affect either method, like these two cases. But then as things become more unclear, the blue method seems to stick to the original label for a larger magnitude of perturbation. So you see here, 8 is preserved here, while 5.5 is predicted by the other approach. And on the bottom line, on the bottom one, you see that 0 is preserved up to this point, and then it turns to 6. So we have less of this interpolation of the prediction when using the distribution robust approach we recommend. Okay. So third framework. And let me, which I think is the most interesting part. I have 20 minutes. Okay. Okay, so the most interesting part. In the previous section, I said you can train your predictor statistically, log likelihood maximization, then use it in the decision model. Now I'll argue that perhaps you should train the predictor so that the decision you obtain from this predictor perform well on the task. Okay? Don't know what this is. It's on your side. Okay. We don't see it because of the caption. This is an illustration of why we should train in this way. In particular, the illustration comes from Elmaktut and Griga in 2022. This is a very important paper called Smart Predict Then Optimize. Here I adapted it. I'm trying to maximize an expected profit, where I use the conditional expected profit, which, because it's linear, becomes conditional expectation of y given x transpose z. The feasible set is this polyhedron, and then the true expected value, conditional expectation, is this arrow. So we see the optimal solution as this, at this vertex. What happens when we estimate, we try to predict this using data? Well, we'll have estimation error, right? So let's say our prediction error leads to this type of conditional expectation. Well, it will automatically get this vertex instead. Although the error is not very large, right? It's a small changes on the right, ends up to a very different solution. Yet if I do an error on the left, I preserve the same optimal solution. So in linear programming, like the shortest path problem, all errors are not equivalent. There is a reason to try to train these predictions so that they prefer certain errors to others, because some errors are actually protected by the fact that the prediction is within the cone for which the same optimal solution will stay optimal. Okay, so this was one motivation for training, having in loss, what are we doing with our decision? Okay. So here's the pipeline. We have a certain parameter theta. This leads to a distribution model that is used in a conditional stochastic optimization problem, which is then the solution evaluated on the data set with respect to our expected cost. This was actually introduced in 1997. Joshua Bengio was training a neural network where the middle box was simply a fixed policy for a portfolio optimization problem, a simple one, and he derived some equations to train the model. In 2017, this was done in Dante et al. For conditional stochastic optimization. And the real difficulty in training these networks this way is when you're trying to find the gradient for improvement, you have to differentiate through H, which is probably okay, but then you have to differentiate through Z star. And this is the argument of an optimization model, which a priori we don't really know how to do. So I'll tell you a few tricks for doing this. If the decision model is convex, we can explore the KKT conditions. So KKT conditions, they give you equations that link optimal solution to the parameters of the problem. And there's this technique, implicit differentiation, that allows you to find derivatives through system of equations. So this can be done. It's very expensive for two reasons. First of all, you need to solve the model for every data point, every time you want to measure a gradient. And you have to solve this implicit differentiation problem, which is demanding. So to try to accelerate, I mean, this is really recent stuff. People are trying to make this training easier and faster. There's ideas around unrolling the operations of the optimization. So if I do just a few steps of optimization with my decision model, and I stop, I can use the operations that were computed in a computational graph and then differentiate through all of them. And this is what we implement with my student, where we don't even optimize to go to optimality. We do a few steps and then differentiate through it. And every time we revisit the point, we try to get a better solution by pursuing from where we were. So this is the ideas behind the unroll the operation. You can also differentiate through fixed point equation of ADMM algorithm. So this is presented here. Final method here is saying you could first train a neural network that mimics this decision model in terms of mapping the prediction into decisions. And then the neural network will be differentiable by construction using computational graphs. The good news is that some of this is already implemented in these libraries. TorchShop, CVXPY layer, PYEPO. There's some strong assumptions of what type of model can be addressed, but these are the first step into making this more of a democratic, accessible to the general field, many researchers. Why should we do this? Well, here are empirical evidence that it's actually working. On the left, we have a model study done by Grigas et al. This is all synthetic, very simple, the network flow problem with 4 nodes. The objective is quadratic. What's interesting here is they have a way in their experiments to control the degree of model misspecification. And the real message there is to say, if your model is misspecified, then the integrated method will outperform the sequential learning and optimization. Because if the model is misspecified, the most likely model is not really representative of the uncertainty to start with, so you could steer it away from the likelihood performance to give predictions that perform well in terms of decision. On the right is more convincing from a practical point of view. They were studying that data from the Ministry of Health and Sanitation in Sierra Leone, managing an inventory model over 1,000 different hospitals. And they're able to show that ILO reduces the proportion of unmet demand by a large amount. The key element here, from what I understand from discussion with the authors, is that they are able to use as covariate the capacity of the hospitals, and this allows the predictions to be perhaps more precise in locations where the capacity is lower, and therefore create less unmet demand than if they didn't take into account the optimization problem that is down the line. Okay, so I'm going to apply this to conditional robust optimization, and I'll spend the rest of my time on this. 10 minutes? 10 minutes. Yes? No? Okay, so integrated learning for conditional robust optimization. So I'm really eager to show you the result of integrated learning that I was able to obtain. But first I have to introduce you to what is conditional robust optimization. And we have all the ingredients in hand. I'm going back to one of my first slides. Stochastic optimization became conditional stochastic optimization and was related to policy optimization. If I'm doing robust optimization, then my stochastic optimization becomes robust optimization, right? I replace the expected value for the cost in terms of the worst case over y. Y being in some set of possible realization for the vector. This is what robust optimization is about. If I have context, I can do the same thing here. I'll replace the conditional expectation by the worst case. Well, what becomes quite interesting and is that I'm using now an uncertainty set that has to adapt to x. The same way my distribution was conditioned on x, now my uncertainty set is conditioned on x. And there's a relationship with policy optimization. So on the bottom left here, I show you a two-stage robust optimization problem where I decide of my mapping for my decision rule. I see first x in some uncertainty set, and then I see y inside a set that depends on x. So this is a flavor of things that are well studied in robust optimization. Adjustable robust optimization has this flavor. And there's a connection between conditional robust optimization and robust policy optimization through, again, this interchangeability argument. But without going into more details, it's one-sided, meaning that I really should be solving the CRO problem instead of the policy optimization problem. Okay, so I'll focus on conditional robust optimization, and I can think of the same three paradigms. But what am I doing? First paradigm is the same. I'm using a policy, so I could just evaluate the policy with the worst case analysis. Here, this predictor, I have to change it. So I'm replacing it by, given a context, I want an uncertainty set that depends on the context. And then this will be used into a robust optimization model. And I have the integrated version. What is the integrated version? I produce an uncertainty set operator. This one is used inside of robust optimization model. The solution is evaluated with respect to a task. So I'm going directly to the result. My task here will be a CVAR minimization. So I have a portfolio problem. I'm worried about the risk exposure. I'd like to minimize the CVAR of the return over the joint realization of y and x. Then here I have constraints on my portfolio. There's no short selling, and I have a total wealth of 1. And I'm comparing here a sequential learning and optimization. So first learning uncertainty set from data, then using it in the portfolio optimization problem. Or integrated, where I'm learning the uncertainty set design in order to perform good on my CVAR, and using this complicated differentiation process to obtain a path for improving my uncertainty models. And you see that in terms of average CVAR, there's a strong improvement in performance. This is about 33% reduction of the average CVAR. The price to pay is the sequential learning and optimization approach is able to give the right coverage. So the sets I obtained from the first approach will cover 90% of the realization, which is what we would ask from these uncertainty set typically. I want a set that covers a certain proportion of realizations. The integrated version doesn't care about this performance and performs badly. Yes?
CVAR is not differentiable at some point. Does it affect your procedure?
We didn't see any problem. We simply use a sub-differential to, yes, the subgradient, yeah. Okay, so we want to recuperate. But the bottom line is that we've lost in coverage. We would like to have best of both worlds, meaning train in order to get good CVAR, but not lose the coverage frequency, right? Because my message here is that I don't think someone will necessarily want to implement my portfolio if I tell him, here's the set, here's the portfolio you should implement, but you're only protected for 23% of the realization. So you might want both good performance, but also some sort of guarantee, or you can claim that this set is supposed to be covering a certain proportion. So to do this, we'll add another loss to our training process, which is related to conditional coverage. And I use this opportunity to introduce you to what are the good statistics about uncertainty sets. You have the figures here to illustrate things. And this comes from a work from Angelopoulos and Bates. So on each of these graphs, I present to you different type of uncertainty set operators. So here's there's one scalar value for y, one scalar value for x. Okay. For any given x, the two lines are giving you the lower bound and the upper bound for the interval for my uncertainty set. Okay, this is the one that is produced by the trained model. Like you're training a function that will give you the lower bound, perhaps, and a function that is giving you the upper bound. Now, there's two different concepts here, marginal coverage and conditional coverage. And what you can measure using data is only marginal coverage. Something like what you see here, you can say that given any data point, what is the likelihood of being inside the uncertainty set? And here you see that a good proportion has been under. It's maybe 90% of the points are inside between the two lines. The issue with this marginal coverage property is I could find some value of x where the portfolio that I will recommend is using an uncertainty set that is 100% covered. Right? You see that the two lines here are completely covering the cloud of points. For other values of x, the interval will be too small. It will only cover perhaps 50%. So this difference between what we call marginal coverage and conditional coverage. On the right, you have both being satisfied. Because for any value of x, you have an interval that covers pretty much everything in the cloud. Okay? Let's say close to 90% of the points in the cloud. Okay, so how do we achieve this? And I'm running out of time. It was complicated. So we first thought of a loss function of this type, where we're trying to minimize the expected value of the square difference between the conditional coverage minus the target. As I bring this to 0, I will encourage the operators that produce uncertainty set that meet the conditional coverage requirement. The issue is that I cannot measure this loss using data. I could use data for this expectation, but data cannot be used for conditional expectation, or conditional probability, unless my data set has, for the same value of x, many different data points that have the same x value. So then I would have a notion of an empirical conditional distribution, but in practice you never have that. So we need to estimate this loss, and we estimate this by replacing the conditional probability by an estimator of the conditional probability. This estimator can be obtained using logistic regression. Okay? So if I have data points, I have an uncertainty set operator, I can verify if the y is inside the uncertainty set. This creates a label 0, 1, and if I do a logistic regression on this, the result is this psi star, which I can use to produce an estimator of the conditional likelihood of y inside the set given x. So this seems interesting. What is even more interesting is that when I allow myself to do integrated learning and optimization, I don't pay a large price for doing this conditional coverage loss objective. So as you saw before, we had a path for computing the loss, which went through the minimizer of the decision model, which was my robust optimization model. Well, I simply have to create a second path where one of the steps is again to create a minimizer, which is my logistic regression model. And given that I have the tool to differentiate through the decision model path, the same tools can be used to differentiate through the regression. Okay, so this is what we implemented. And I go now in more details here of what was the experiment. So this experiment was with a joint Gaussian mixture model with two modes. Each x and y have dimension 2. So on the left here, you have the heat map represents the marginal distribution x1, x2. You see there's two modes, and the star is giving where am I conditioning. So what's the context I'm observing? This animation is showing the effect on the uncertainty set that are produced. On the right, you see the space over the dependent, which is the y1, y2, perhaps the returns of two assets that I'm investing in. And the heat map is the conditional distribution given that x is the star. And you see that this conditional distribution goes from one mixture to the other depending on where the star is. And you have three different sets. The sequential learning is green, the integrated learning is blue, and the integrated learning with conditional coverage is red. Right, so what I want you to notice here is, yes, as x is changing, these sets are moving. The blue set never really covers the distribution. And that's because it was never the intention. We had 23% coverage last time we looked at it, on average when we sample X. The red set does recuperate. It might even overcover. But in robust optimization, we don't care that much if we're overcovering, as long as we have the guarantee. So did we lose anything in terms of performance? This is the new row in our table. So we recuperated a coverage that is very close to 91%, 90%, and the loss in terms of CVAR is minimal. Okay, so the optimization of the uncertainty set was able to jointly optimize the CVAR and the conditional coverage, and perhaps provide sets that achieve both a good performance in both cases. This is all synthetic, right? We know the underlying distribution. We're hoping, I mean, you could do this analytically, producing these results. It's not so impressive. What's impressive is to be able to learn this from data directly. What happens if you deploy this on a real problem? Here we have a portfolio optimization problem with market data. The contextual information, there's a list over here. So we have trading volume of the asset, volatility index, we have treasury yield index, which allows you to monitor the interest rates. We have an oil index, S&P 500, gold price, and Dow Jones. These are all like sort of macroeconomic indicators that we're trying to exploit to find what is the best portfolio for the assets. And the assets that we're investing in are 70 different stocks. Okay, so these are not the stocks we're investing in here. It's 70 different stocks. And there's a period for training. There's a period of testing. We're testing over 2017 to 2019. I present here only 2019 result. So depending on the target, 1 minus epsilon we use, we're able to train these things so that the coverage is accurate. So we get very close coverage for the methods that are meant to give the coverage probability. And if we look in terms of performance, we can look at maybe just the 90% confidence level. So here we're asking the method to produce a set that covers 90%, and it's good with respect to 90% CVAR. And we see that it seems statistically significant that as you go from sequential learning to integrated learning, there's a performance increase on the real data. And this is all out of sample. So you see this is about the same type of performance increase as you change the targeted confidence level from 70 to 90%. And the same results are similar for the other 2 years of test. So I come to a conclusion. I hope I didn't run too much out of time. So first, the main message would be I wanted to get you interested in contextual optimization. So if you lost track of what I was trying to present along the way, so there's an active field. I think it's really nice how this field is integrating machine learning, optimization. There's a lot of space for new discoveries. And I mean, it's really a point of intersection for scientists that are doing machine learning, data science, and at the same time, people that are really fascinated by optimization and modeling decision making processes. I presented 3 different types of approaches, going from decision rule optimization, sequential learning and optimization, and integrated. Today, I only talked about 2 ways of training these models, this prediction model: statistical accuracy, like my coverage probability, or task-based, which is trying to minimize the out-of-sample CVAR. In the literature, you'll see a rich amount of papers talking about regret, trying to minimize regret. And I think what is also equally interesting is trying to predict models that produce decisions that are close to decisions that are observed in practice. Because I think for adoptions of our prescriptive models, we cannot bring the decision maker too far from things that he's already doing. And perhaps what he's doing accounts for a lot of things that cannot be modeled in our optimization. So having a trade-off between 3, or at least 3 of these 4 objectives, I think is important. There are many potential applications. And finally, there's also, it's a fertile ground for robust optimization and improving the robustness and also the risk mitigations in these problems. There's a list here of 25 papers that I didn't talk about today, but they're all under this umbrella of robust optimization for contextual optimization. And this is just the last 6 years or so. So very, very active field and interesting findings. And I have to thank my collaborators, the students involved in these projects. So I have this slide with a timeline, approximative timeline. There's 6 papers involved on this topic. I presented some of them. The part that is here is the research program that we've been running for the last 2 years and that we're trying to extend in the future on the integration of machine learning and optimization for decision-making under uncertainty for supply chains. You'll see this will rotate ad infinitum with the QR code showing you links to websites you can go see the material. Thank you for attending and your questions. I'll take any questions or comments that you have.
Thanks, Eric, for a very informative talk. So, any questions from our audience? Yes.
Yeah, I actually have many questions, but maybe I'll just ask 2 of them and maybe take further offline. So for the last part about CRO, and so in CRO, I think the kind of the shape of these ambiguity set also matter for the subsequent optimization problem to be tractable, right? So I just wonder, like, judging from this very nice animation that you show, it seems like it's always like this oval or maybe in high dimensional ellipsoid sort of shape. Is that sort of hardwired into this design of the predictor?
Currently, we didn't go into the details. So it would be a complete 1-hour talk, even because of the extent of the work we did on this topic. We were encoding the ellipsoidal set here. So the neural networks we were training were predicting the mean of the ellipsoid and the covariance matrix that would be used for the shape of the ellipsoid. So it's not that it would be encoded in the model that we obtained ellipsoidal set, which was beneficial for the downstream decision model and being able to train this in an integrated fashion, indeed. If you start having more sophisticated sets, and we have work where we use neural network to produce these sets, and they can produce completely non-convex, disconnected set, but it's not clear how you would integrate this with the decision model. Because solution, it can be very hard to obtain and so on.
And my other question is about the IRO part. If it's not too troublesome, can you go back to the slides where you have this linear programming example where sort of, not all errors are the same for the downstream optimization problem? Yes, I think. So here, I think you're trying to say that, okay, it makes sense to favor errors in certain direction over maybe a different direction, right?
Yeah.
But I think in the next slide also, you jump to the part where you directly learn the mapping from the context to the final decision, rather than sort of this error in the sort of the prediction of the Y. So is there something that I missed? Maybe I sort of...
That I ignore?
Yeah, this? No, I'm just trying to understand the relation between these slides where you're trying to say that if I first predict Y, right, and there's sort of certain direction of error that's more favorable than other direction, but then later I think in IRO, you're directly mapping from X to the final decision, and kind of, if I understand correctly, skipping the step of predicting Y. So is there some...
Then I didn't explain properly, because the point here is that if you consider 2 different models for this, theta 1, theta 2, they might both have the same error from the point of view of likelihood, but when you're passing these models inside the Z star, it's possible that one of them, although it has the same error, will produce the optimal Z star for X. In the sense that there might be error in the model, but at the output for a given X, you might still have the same solution as if you knew exactly the model of the underlying conditional distribution. And this you will only recognize by testing on the task loss, because you would realize one of the model is going to a suboptimal solution, and when I plug in the task loss, I get a higher cost, while the first one with the same error would have this good performance on the task loss. So we're able to backpropagate the signal to encourage some parameters that create perhaps errors, but errors that don't affect the optimality of the solution. Yeah.
Thank you for the clarification. I find this part very interesting because I somehow dabble into a problem that has similar phenomenon that's on like learning optimal auction from data, where you also have like it's sort of safer to underestimate, because if you, let's say, set the price a little bit lower, You know, the revenue is not going to drop by a lot. If you overprice, then if the buyer change from buying to not buying, then it's actually a much bigger risk. So yeah, so kind of we also face this problem of like not all kind of errors are the same, and you kind of favor one kind over the other kind. So that's why I find this part very interesting. Thank you.
Great.
So Eric, we have an online question. I'll read it for you. So in SLO, without the real distribution, how to set the loss function and determine the distribution obtained from training converged to the optimum?
Without the true distribution, how do we show that it converges to the optimum?
Yeah. I speak again. So in SLO, without the real distribution, how to set the loss function and determine the distribution obtained from training converged to the optimum?
This is a little bit outside what I can answer today, but this would be results from statistical learning theory. Like I guess the question is pointing at what are asymptotic convergence theories that says that as n goes to infinity, then this loss function would return f theta, a theta that is converging to theta star, assuming that the true distribution model is inside the class. Of course, if the class is misspecified, this will never happen. But if you can assume that the theta is inside, there's a theta star makes f theta star equal to the conditional distribution, the hope would be that you can converge there. And I don't have top of my head what are the literature that are guaranteeing this, but it's behind the analysis of this estimation problem, indeed. Yeah.
Yeah.
For your experiment with MNIC or MS data, I was just wondering, you said the training data to just 100 points. Could you just elaborate a little bit more on that? Like why just 100 and what happens with the experiments? Let's say, are the trends consistent if you scale it up a little bit more? Let's say 200, 1,000 or something.
It's been a while since I looked at the result of these experiments. This would be here, right? We focus on low data regime. I explained why we focus on low data regime. Like in high dimension, if you have a high data regime, then I think these numbers somehow are in the end, you have enough data to find another image that looks very similar to the current image. So in that case, k-nearest neighbor might already perform very well, like in the 80, 90% perhaps accurate labeling of the test set. So this is why the result I present here is not necessarily very relevant for handwritten digit recognition, but it's a really nice environment to be doing these data-driven tests and showing that if you only have a few labeled example, which sometimes this is the case because labeling is expensive or things are non-stationary, so even the labels from last week are not very useful this week, and that's a case where perhaps you would have a very small amount of training data. Now you're saying, is this, what would be a comparison study where we look at the sensitivity of the number of training data point? I don't have right now at the top of my head where do these methods, at what regime do these methods become somehow equivalent to each other? But it's an interesting question indeed. Yeah.
No, that's fair because I think a lot of people always talk about data-driven methods, and I'm one of those where I absolutely hate using too much data, so I'm really glad that there's only a few data points used. Yeah. Thank you so much.
I have a simple question. So normally sometimes the contextual information is not quantitative measurable. So is there any proper methods to mapping the so like whether those things into quantitative numbers in order these methods can be applied?
This is an ambition with this work, especially in the context of portfolio optimization. We tried 2 years ago to learn from text data. In text data, you don't have numbers for that. It's not quantitative. But that's the advantage of perhaps using deep learning methods or trying to learn embeddings of the of the covariates that are useful for decision making. And so we were a bit ambitious initially, trying to directly go to this type of unstructured data and learn from it, and we're unsuccessful. Now, a few years later, with more methods in hand and more experience, I would be very happy to go back and see whether we can use unstructured data more seriously. Yeah. You can think about like your weather. You could have just a heat map of the weather in different locations of town, or the amount of rain and so on, and this just from the heat map infer all the information about what is the travel time on the Ozark and so on. That would be great to see something like this work. Yeah.
I'm outside of this field, but I have a question about how to account for the dynamics of the conditions or context, because the context could be evolving, right? So, say the weather forecast, or it could be the future dynamics could also be dependent on your decision at this point, like the traffic problems. So, to my understanding, currently the incorporation of the context is mostly a static like solution, right? So how to account for the dynamics or evolution of the context?
Yeah, it's an excellent question. In fact, I think this contextual optimization field has tried to focus on static problems instead of dynamics one, because very quickly when you start thinking about dynamics of your context, dynamics of your the effect of your action on the environment and so on, you end up playing in the field of reinforcement learning. So in order to distinguish, I think, the two types of field, and thinking maybe there are methods that are specifically tuned for static problems and that don't really apply for reinforcement learning, but perhaps also the methods were designed for static problems can have interesting implication for dynamic settings. I think this is still underexplored. Like we can still make some progress in understanding how to extend these methods to dynamics, or maybe how to import more reinforcement learning approaches in the context of static problem, perhaps.
Thank you.
Thank you. Okay. Is there any further question? Okay, so if there's no, so let's thanks Eric again.
Thank you.
Thank you.
Thank you.
So this ends our Ideas Distinguished Speak series today. Thank you.